We're moving to Kamal Kadari, who will tell us about how we're actually getting to the pyruvate that we can use to look at cells and then work with that on, say, a benchtop. So, Kamal, are you ready?
Yeah, I'm ready.
Very good. We can hear you well. Feel free to start sharing your screen.
Awesome. Is
Yeah,
it working?
go ahead. I'm looking forward to your talk.
All right, awesome. So, hi everyone. First, I wanted to say thank you for the opportunity, of course, to speak at the Perm conference. A special thank you to my PI, Professor Shakmanev, for letting me be part of this. It's a privilege to share our bench to cells workflow with this community. So, I'm Kamal Kadari, an undergraduate pre-med student at Wayne State University. The work I'm showing today was performed primarily at the Kermanos Cancer Institute. The goal of this talk is to do a show and tell of our bench to cells workflow for generating SABRE hyperpolarized C13 pyruvate on a 1.4 Tesla benchtop NMR and then delivering it to live cell suspensions. So you just saw the lactate formation of hyperpolarized pyruvate in various cell lines. My focus now is how we enable that reliably, covering the the batch prep, the activation, rapid processing to biocompatibility, and dynamic readout. So let's start at the very beginning. So we built a 10 ml batch protocol for consistent starting materials. First, we weigh the iridium at 69.1 milligrams, sodium C13 pyruvate at 77.7 milligrams. Now, because pyruvate and the catalyst are oxygen sensitive, we move this into the argon chamber as displayed in the presentation. Next, we add the DMSO slash D2O to reach the stock target, which would be 10 ml of 120 millimolar DMSO and D2O, which is 2.22 grams, and we combine this with the pyruvate and the catalyst. We close the vial loosely, then run two inerting cycles, evacuate to negative PSI, close, backfill with the argon, repeat. This rapidly, of course, drops the oxygen exposure. Finally, we tighten the cap, and the batch is ready for storage. And now I'll show how we package this, dissolve these stocks for polarization. So you can see here we store each alkylate in a vial arrangement, a glass inner vial inside a second container. The purpose of this is a double layer of argon atmosphere around the inner vial to keep the catalyst as isolated from oxygen as possible before actually using it. When we're ready, we of course thaw it, add the acetone 6.275 grams of it to reach the working solvent ratio, and then we sonicate to fully homogenize. This pretty much ensures the substrate catalyst and DMSO are perfectly mixed, so activation curves are repeatable. And this clip right here is just 11 seconds. But the point is, homogeneity up front makes everything downstream faster and more consistent. Moving forward. So with these materials already, here's the actual physical layout for the biocompatible processing. So on the left over here, you'll see the control PC running the SpinSolve Expert software for live acquisition. On the right of that is the SpinSolve 60 1.4 Tesla for C13 readouts. And then on the right at the very bottom, you'll see the parahydrogen cylinder right underneath the mobile SABRE polarizer, which houses of course, the activation zone with the shielded region for that control field exposure. And at the very top, you'll see the zero point 0.2 Tesla processing magnet used during extraction to mitigate any polarization lost during that process. And this overall compact layout minimizes movement and time between our steps. So now we can move on to the actual polarizer in action across these three little clips. Yeah. So in clip one, we load 0.6 ml into that jacketed 5 millimeter tube with the bottom reaching catheter, pressurize it, and then place it in that 7 degrees Celsius bath for 90 seconds to stabilize temperature. Yeah. Clip two, we start the activation of the actual parahydrogen at 100 SCCM upon that temperature stabilization. And the final clip, you'll see us cycling the tube to the spectrometer for that quick C13 readout, basically checking pyruvate integral as polarization builds. So next we can see how stable are the actual starting materials. We tested fresh and frozen. So this plot basically shows activation trial number versus that C13 pyruvate signal for a fresh batch and a batch that's frozen for 2 months at 20 degrees Celsius. So the curves are nearly overlapping, so freezing does not penalize polarization in our workflow, and that, of course, enables batching and predictable scheduling. So we also benchmarked formulations for to maximize polarization. So here we compare maximum polarization across pyruvate concentrations from 70 millimolar all the way down to 70 millimolar all the way down to 3 millimolar. So as the concentration decreases, the observed max polarization increases. For example, 70 millimolar is lowest in the set, while that 3 to 6 range kind of is at the highest. The trade-off is very clear. Lower substrate boosts polarization. However, it reduces the delivered moles on injection. In practice, we will choose a concentration that balances signal and dose given our cell volume and timing. But of course, once we hit our target polarization, we will convert these samples for cells. So this about 42-second clip shows the rapid processing. So here we'll see how we remove the activated pyruvate from the shield, dock it, and then using butyl acetate, we perform this kind of push-pull extraction through that junction, pulling the acetone and iridium catalyst into the organic phase, and then the aqueous hyperpolarized fraction goes into that collection tube. We'll see right here, and then it's positioned near that, of course, that zero point 0.2 Tesla magnet. And we give it a brief parahydrogen bubble for 14 seconds to strip any residual acetone. And then upon the completion of this 14 seconds from here, we draw the process hyperpolarized pyruvate and inject it immediately into those cells that are waiting in the spectrometer. This whole sequence is designed to be fast, field discipline, bringing as much polarization as we can into the biology. So now let's look at the dynamic readout in cells. So right after injection, we run 200 scans with 10-degree pulses every 3 seconds. So in this video, you'll see pyruvate near that 169, 170 ppm kind of decay as polarization is consumed and metabolized. And then around that 182.5 ppm, you'll see the lactate kind of rise via the LDH conversion. So on the left, you'll see the cell suspensions, 30 million leukemia cells in 0.3 ml, 25 million BRCA cells in 0.3 ml, each in 5 millimeter tubes. And of course, it's 37 degrees Celsius pre-equilibration kind of standardizes metabolism across all these runs. Though the clip is short, it's key to seeing that opposing pyruvate down, lactate up trajectories we quantify. So now to move to normalize the actual biology, we need to know exactly what the cells received. So after extraction, we run high field NMR on the remaining aqueous to measure the pyruvate concentration and to check residual acetone. We build a calibration curve with ethanol standards, and then we acquire seal ethanol standard with every run. So in the proton spectra, pyruvate you can see at 2.31 ppm, acetone at 2.17 ppm. Why do we need the pyruvate concentration? The hyperpolarized signal we minimally detect is proportional to the concentration of polarization. So knowing the concentration lets us basically quantify that polarization, which enables run-to-run normalization because input polarization can vary between runs. We then normalize these dynamics by delivered pyruvate and effective polarization. So the lactate trajectories are directly comparable across multiple days and formulations. So moving forward, we now have, we also document the cell density and viability for each run. So on the left, you'll see the biosafety cabinet where we make the PBS serial dilutions at 900 microliter tubes, A and B, add 100 microliter cells to A, which turns into 1 to 10 ratio, then 100 microliters of that whole thing into B, which turns into 1 to 100 overall. So for these manual counts, we mix 100 microliter diluted cells of this whole process into another 100 microliter of trypan blue, load the slide, and then do a microscopic count. In parallel on the right, we see how we prep the counter slide and run an automated A and B runs for a standardized readout. So why quantify cell density? Of course, because cell concentration directly will impact the apparent pyruvate to lactate rate. Normalizing the cells per ml pretty much helps us keep the metabolic readouts comparable. So here's what these readouts look like, of course, post-processing. So on the microscopic image, we can confirm by manual counting. And on the countess, you'll see on the right, which is the green, which is, of course, the live cells, red, which are the dead cells, with the dilution corrected concentration and viability. So agreement between both of these methods kind of gives us confidence in our biological baselines for each of our NMR runs. So I'll close with what we built and where it's going. So we developed a manual end-to-end workflow for producing hyperpolarized C13 pyruvate and delivering it to live cells on a benchtop system, from batch sample prep to activation to rapid SABRE processing, ending with that dynamic metabolic readout. Crucially, the pipeline enables, of course, normalization, as mentioned before. We control deliver pyruvate, effective polarization, and of course, the cell density and viability. Limitations and next steps. We move toward automation to reduce operator variability and increase throughput, but the expand to in vivo settings where timing, dose control can become even more crucial and critical. But overall, yeah, thank you so much for your time, and happy to take any other questions.
Yes, Kamal, thank you so much for that beautiful presentation.
Yeah.
As I said again and earlier, feel free to put your questions in the chat. So I've been wondering about a few things here, but first of all, I would like to say, interesting to see that we can just freeze our samples and use them over and over again. That will be so useful long term, and you building all your own inert gas chemistry. That's really nice. So I was wondering what's limiting your polarization if you go to higher concentrations? Is it just the hydrogen? Are you already at the maximum pressure you feel comfortable going to?
Um, so I think I briefly kind of touched on this where I said that we we adjust the concentration of pyruvate depending on what we're exactly using, what cell and what cells we're using and whatnot. Is that what you're exactly asking, or?
Oh, I mean, the polarization you're getting at higher pyruvate concentrations is lower, yeah? There will be some reason for that.
So I guess polarization is like mainly limited by the balance between like I guess transfer rate and relaxation. I think the parahydrogen spin transfers the pyruvate only when it's bound to the catalyst complex. So if exchange is I think too slow, you might lose efficiency. If it's too fast, then it decays before. And I think at the T1 relaxation and like magnetic field mismatch and residual oxygen, the that caps like the achievable polarization, if that's what you're asking.
Okay, so you have relaxation losses as you increase the catalyst concentration, is what you think. Okay.
Yeah.
Uh, and then I was wondering, you're doing all these cell experiments. To me, that sounds like a lot of work. How many of these can you do on your day? You say you are manual counting, you're using the counters, you're running the benchtop. How many hands do you have to do all this?
Yeah, no, we when we first started we were doing about like six experiments per day, and then we upped it to 8 to 12 experiments per day. We have like a pretty solid team that works. We built a very good protocol of making sure everything works well, and then we're able to achieve everything we need starting from the morning to the end of the day.
Oh, I see. So it's a big team effort. Yeah. Thank you so much again for that wonderful talk. Let's give you a big round of applause.